See, now it's not giving me a countdown. Now it's just putting me right into it. I don't know. Last period, give me a countdown. Whatever. Here we go. Okay, so now we're going to get into chapter 2. I am so excited to get into chapter 2 because this is like actually calculus. Like everything that we've done. That look. Oh. Because everything that we've done up until this point has been review, right? Everything that we have seen has been like, oh yeah, well, we've at least seen that before. Now we get into stuff that you've never seen before, which I think is fun. You know, like there's still stuff in math that you've never learned before. That's so cool. All right, so section 2.1, to introduce this stuff, the book gives 2 problems that we will kind of relate back to the entire chapter. Okay, and yeah, we will be within this chapter probably, I mean, at least throughout the whole month of October, probably maybe a little bit into November, but then we start into chapter 3. Okay, so section 2.1 is called the tangent and velocity problems. We're going to talk about 2 problems today. The first one being the tangent line problem. And again, I will refer back to this at many points throughout the chapter. Today is not going to be a lot of like handwritten notes. It's going to be a lot of conceptual stuff, a lot of just like, okay, think through this with me. Okay, so the word tangent basically means lies next to. It's a Latin word meaning touching. So basically what we're going to be looking at is when something lies next to something else, right? The word tangent means lying directly next to. We're going to go with more of the geometry definition of tangent rather than the trigonometry definition of tangent. Okay, trigonometry being the opposite over adjacent side of a right triangle, where geometry side of it would say, okay, if you've got a circle, and I think the diagram is down below, if you've got a circle, a tangent line would be one that lies directly next to that circle, where there is only one intersection point. Okay, kind of like you think about the circle bouncing off of that line. Okay, in other words, a tangent line should have the same direction as the curve at the point of contact. You know, it's interesting to point out that we're going to be talking about the same direction. Yeah, kind of saying that maybe the tangent has a directionality to it, a point, like almost like a vector, like it's going somewhere, right? We're going to be referring back to that a lot as well, because you can talk about a line being tangent from one side or the other, right? You could say like left side or right side, okay? So what we're going to be looking at is how can we make that a little bit more mathematical? How can we make that definition a little bit more precise? So we don't just say, okay, it's going to touch the curve. But how do we really say that? How do we say that in terms of our algebra brain? You know, for a circle, we would simply follow Euclid and say a tangent is a line that intersects a circle once and only once. That's our like geometry definition, right? Where it's going to intersect the circle once and only once. It's going to just basically touch the circle. It's not going to go into the circle. We would call that a secant. It's only going to just touch it once. It's going to lie tangent to the circle. Okay? But would that definition hold for something like this? If would our geometry definition, where I said it's going to intersect the circle once and only once, does that hold for our curve? No, because it doesn't intersect once. It intersects twice. So what we're going to be looking at is, okay, how do we specify that a little bit more? How do we be a little bit more specific? Okay, the line L intersects C only once, but it certainly doesn't look like what we think as a tangent, right? It doesn't. It's not a tangent right here, is it? No, it's going directly through there. So how do we say, well, this would be the only tangent and that's not a tangent, right? Because that's intersecting once and only once, right? That our geometry definition saying it intersects once and only once doesn't hold right there, because it intersects twice and that point right there is going straight through it. So how do we mathematically say, well, it's not going to go straight through, but it's going to go like off the side of, almost, right? To investigate this, let's take a look at x squared. Find the equation of the tangent line to the parabola y is equal to x squared at points 1, 1. Interestingly enough, by the end of chapter 3, you will probably be able to do this question in about 30 seconds. We're going to look back at this question and be like, oh, little did we know what was ahead of us. Okay, find the equation of the tangent line. And honestly, that premise is going to be, I would say, on your Chapter 3 test, like 60% of your problems are going to start with that. Find the equation of the tangent line. There's reasons why we find the equation of the tangent line. We don't know context yet. But that's really what we're going to be looking at for a long time coming. Okay, so now, we've got find the equation of the tangent line to the parabola y is equal to x squared at the point 1, comma 1. Notice that I defined where I want it to be tangent. Right? I have to define where you want it to be tangent. Because if I think about the parent function quadratic, what diagram do I have? Okay, yeah, I don't want to show that yet. If I think about the parent function of the quadratic, like where do you want it tangent? Do you want it tangent here? Do you want it tangent here? Here? So you have to define where the point of tangency is. So let's do that. We will say that it's at 1, comma 1. We'll put a point right here. Move this over just a little bit. There we go. Meet my needs. So 1, comma 1. We are going to find the equation of the tangent line at point 1, comma 1. This is our goal. Oh. Okay, I have to bring this down a little bit and bring this over. Sorry. I want to make my picture good so that when I go to explain it, it's okay. Okay, there we go. Yeah, there we go. Looks good enough for me. Our goal is to find the equation of that line. Now, in the end, shouldn't I end up with like y equals mx plus b, right? Like I should get a slope, and I should create the y-intercept based off of any point that I have, right? Okay, now, here's what I have here, right? I want, because if I wanted to have this y is equal to mx plus b, the most important piece of that equation is going to be our slope, right? We could find the y-intercept given 2 other points, but we really need the slope. That's the key to unlocking this whole equation. So if I wanted to find the slope, well, what points do we have? We have 1, comma 1, but we also have this line. And I know any input would be x, and the output would be x squared. You follow me? That's just the equation. I input x, I get out x squared. That's just any coordinate. 1, comma 1, 2, comma 4, 3, comma 9, 4, comma 16, right? I'm generalizing it to be any coordinate, any point. Okay, so if I wanted to find the slope, I could take y2 minus y1 over x2 minus x1. X squared minus 1 over x minus 1. X squared minus 1 over x minus 1. Y2 minus y1 over x2 minus x1. Just running the slope formula, right? Okay, now, take a look at what's going to happen here. If I take points, and I say that I wasn't really sure where this was going, what the slope was going to be, let's get an estimate by taking 2, comma 4. Let's put this in green. 2, comma 4. I know this is just an estimate because if I draw a line in here, I know that's not tangent, but it's going to give me an overestimate of the slope, right? Isn't that going to give me an overestimate of the slope because it's a little bit steeper? So let's see what that comes out to be. 4 minus 1 over 2 minus 1. And that's just plugging those into our formula, right? I really need the y value. Just plug in the x value. 2 squared minus 1, 4 minus 1 over 2 minus 1. So 3 over 1, so 3. But that's pretty far away, right? What if I wanted to bring this point closer? If I brought this point 2, comma 4 a little closer to 1, comma 1, wouldn't that give me a little bit more precise of a slope? Like, wouldn't that slope get closer to the true slope? Okay, so maybe let's plug in, so this was 2. So maybe we should do 1.5. Let's see what happens. 1.5 squared minus 1 over 1.5 minus 1. X squared minus 1 over x minus 1. 1.5 squared minus 1 divided by, and then 1.5 minus 1 would just be 0.5. 2.5. Still not very accurate, is it? Maybe we should try 1.25. Now, do we all understand why we can't just plug in 1? What would happen if I plugged in 1 to this thing? It's not in the domain, right? Bottom turns into 0. So I know I can't plug in 1. I know I can't go like 2, 1.5, then directly down to 1. So what if I plugged in 1.25? 1.25 squared minus 1 over 1.25 minus 1. Let's see what happens. 1.25 squared. Nope. Oh, thanks. Get out of there. 1.25 squared minus 1 divided by, and then 1.25 minus 1 would just be 0.25. 2.25. I could repeat this process for days and days and days, right? I could repeat this process getting closer and closer and closer to 1. 1.1 squared minus 1 divided by the difference in the x's would be 0.1. 2.1. Okay, so I went from 3 to 2.5 to 2.25 to 2.1. What am I getting closer to? What am I getting close to? 2. We could guesstimate that it's probably going to get to 2, right? Let's run one more number and see how close we get. Let's say instead of 1.1, let's go like really close. Let's say 1.00001, right? So let's put 4 zeros in front of it. Squared minus 1. And then I'm going to divide that by, okay, so it would be 1.00000 minus 1, right? So really just the differential on it would be 0.00001, right? 4 zeros? Okay, good. Ooh. So I can almost confirm the fact that it's going to get really close to 2, right? Okay, so we believe that the slope is going to approach 2. Did it ever actually reach 2? Did it ever actually get there? No, but we believe that it's going to get there, right? That we believe that all signs point to 2. Now, I went from the upper side of this, right? I went from an upper estimation, like an overestimation, excuse me, right? So what if I wanted to go with an underestimation? What if, say, I wanted to start from the point 0, 0? Wouldn't this give me an underestimate of the slope? Okay, let's do that. Okay, so if I start with 0, that would be 0 minus 1 over 0 minus 1. Okay, so that's just 1. We know 1 is an underestimate, which makes sense because we believe it to be 2, right? We know 1 is an underestimate. So what if we went to 0.5? What if we keep getting closer to 1, but just from the bottom end? Well, that would be 0.5 squared minus 1. Now, the denominator is going to be divided by 0.5 minus 1, right? So negative 0.5. 1.5. Okay, so it makes sense. I'm growing a little bit. What if I jump to conclusions here and said, I want to get really close to 1, but from the bottom end. Let's say 0.999. Let's run that value. What do we think it's going to come out to be? Probably something like, the slope's probably going to come out to be like 1.999 something, right? At least that's our estimate. That's what we think might happen. 0.999 squared minus 1 divided by, okay, so 0.999, right? I'll just do this. 0.999 minus 1. Ah, yes. We believed that it was going to come out to that, and that was the case. Okay, so we are saying from the top end going down to 1, it looked like it was going to go to 2. From the bottom end, also going to 2. Okay? This, what I have hidden over here, is just more points that run that exact same thing. Okay, basically what we just did by hand there. This is the diagram the book gives. They're denoting it as MPQ. This notation is saying that it's finding the slope using 2 points really close, right? Not necessarily finding exact slope of the tangent line, but believed to be slope, right? Some slope that could get really close to. And they saw, okay, once they ran 2, 1.5, 1.1, 1.01, and 1.001, and found that it kept getting closer and closer to 2. And then they did that exact same value from the underside, the exact same process from the underside, 0, 0.5, 0.9, 0.99, 0.999, and saw, okay, slope got really close to 2 just from the underside. So we can make the conclusion that the slope of this tangent line is going to end up being 2. So let's make that conclusion. Let's say slope is 2. All signs point to slope being 2. And we have the point 1, 1, right? We started this problem by saying it needs to lie tangent to the curve at 1.1. So let's create the equation of the tangent line using those two values. Y minus, I like to go through point slope. Y minus 1 is equal to 2x minus 1. And just for fun, we'll put it into points or slope-intercept form. Sorry, I forgot my minus 1. 2x minus 2, and then we'll add the 1. Y is equal to 2x minus 1. There. That is the equation of the tangent line. Now, that process was really a big, we had to make a big jump. I mean, maybe it wasn't a big jump for your guys' heads, but for me, like, my math brain was like, so we're just going to trust the fact that we think it's going to go there, so we just say it's going to go there? Like, that seems really Bush League. Like, that seems really like, are we allowed to do that? Not really, but that's what all of Chapter 2 and Chapter 3 is about. Like, how do we make that a concrete, yes, the slope is 2? And again, we can look back on this in like 2 months' time, and you're going to be like, oh, we can do that problem super easy. Here, done. 30 seconds. Okay. But that's the ending point here. The equation of the line is y is equal to 2x minus 1. How did we do in our graph? How did we do in our diagram? Okay, not bad. Here was my tangent line. Look, y-intercept being -1. Okay. Slope of 2. Yeah, sure. That looks like a slope of 2. Graphed it generally correctly. Yeah. I kind of talked through this as it went, but they're talking about how I can bring this point, here's 1, 1. I can bring this point closer and closer and closer to P. Yeah, that's the process that you're going to use in the homework, where I am going to take a point and I'm going to make it closer and closer and closer to that value to see what the slope turns out to be. Now notice that you could do it from the left or from the right. This was approaching it from the right, right? That point was on the right side of the actual point of tangency, but I could use it also going from the left side as well. Yeah. It's going to lead you to the slope no matter what point you choose from the left, as long as you keep making it closer and closer and closer. I'm going to bypass this problem. We're going to go straight to this problem. Okay, so that was the tangent line problem. That was the tangent line problem. We're going to find equations of tangent lines many, 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 many times. Okay, let me shut the door here. Okay, now this next problem, it's not going to seem like it relates. You're going to be like, this is out of left field. What the heck are you talking about? But honestly, it's like the exact same process. If you watch a speedometer of your car as you travel in city traffic, you see that the speed doesn't stay the same for very long. That is, the velocity of the car is almost never constant, right? Even when you're on cruise control on the highway, right? Your car slows down a little bit, and then the cruise control picks it back up again and speeds it back up, right? It does it very minutely. You don't even realize it's happening. In your brain, you're like, yeah, I'm just going at a constant speed. Yeah, that's for your purposes, yeah, you are, but the car is not actually doing that. It's slowing down a little bit, then it's kicking the engine out and speeding you up, and then slowing you down, then speeding you up, then slowing you down. We assume from watching the speedometer that the car has a definite velocity at each moment. But how do we obtain instantaneous velocity? That That instantaneous velocity is something that we're going to be trying to calculate throughout the entirety of chapters 2 and 3. Instantaneous velocity. Instantaneous velocity. Let's investigate that by this example of a falling ball. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto. I actually saw that this summer. We went to the CN Tower in Toronto. Pretty cool. You can see it from like across Lake Erie. It's really cool as you're like coming around in Canada. Anyway, I digress. It's 450 meters above the ground. Of course, it's in Canada, so they use meters. Find the velocity of the ball after 5 seconds. Okay, now, I am not saying find the initial velocity. I'm not saying find the final velocity. I am saying find the instantaneous velocity. How fast is the ball going at 5 seconds, at that moment, okay? Now, speed is, well, how do we calculate speed? Change in distance over change in time, right? That's speed. That's, in a nutshell, that's how we calculate speed. Change in distance over change in time. Velocity is difference in distance divided by difference in time, right? Delta, I'm using my science brain here for delta. Delta D over delta T. Change in distance over change in time. That's going to give you velocity. That's going to give you speed, right? Okay, well, think about it this way. You know, I know any falling object is going to have this equation, 4.9 t squared. Right? 4.9 t squared. That's 1/2 at squared for my physics people. 1/2 a. What is a here? What is acceleration? Gravity, right? Acceleration due to gravity in meters per second is 9.8. So 1/2 9.8 is 4.9. So that's where that equation comes from. Now, so 4.9 t squared is our equation. That's how fast. That's the position of the ball, s of t. Okay. Now, if I want to calculate change in distance, what I'm going to do here is I'm going to calculate change in distance in relation to the time I'm looking at. Like, for example, from time 5 to 6, okay, I'm going to calculate speed, average speed over the time period 5 to 6 seconds. That's a big gap, right? A whole second? Like, that's a lot. I'm going to be changing a lot within that second, right? Okay. So if I know change in distance, well, change in distance. Oh, don't look at that. Hide you. Don't let the cat out of the bag, man. Okay. All right. So change in distance. This is position, right? Okay. So change in distance is change in position. So I'm going to say 4.9 times 6 squared minus 4.9 times 5 squared over change in time. What's my time interval? 1 second. Right? Okay. So let's go. Oh, you know what? Oh, that's okay. That's all right. 4.9 times, I'm doing things different from my key, which is always never a good sign, but I think I'll be all right. 53.9. Yeah, okay, good. 53.9 meters per second. Now, but was that instantaneous velocity at 5 seconds? No. So how can we make this problem a little bit more precise? Well, let's change up our time interval. Let's not go from 5 to 6 seconds, but 5 to 5.5 seconds. You see how this is very similar to my tangent line problem? So 4.9 times 5.5 squared minus 4.9 times 5 squared. And now my time differential, my difference in time, is only 1/2 second. 51.45. Okay. What about time? Let's just jump to here. Because I know it's going down. I can't recognize a number that it's going to go to yet. I should keep running values till I see it. So difference in distance, 4.9 times 5.1 squared minus 4.9 times 5.1. Oh, shoot, darn it. Hold on. Forgot my squared. I knew I did it. Oh, wait. That's what I did wrong. Did the point ones twice. Delete. Delete. There we go. Ah, there it is. And then I divide that by, now what's my time differential? 0.1 seconds. 49.49. Okay, so I'm still going down. I'm going down at a less rate now, though. Maybe I should run it one more time differential. Let's go crazy. Put 2 zeros in there. Let's go crazy. I'm going to go back to this calculation and say I'm going to add in, insert 2 zeros. And now my time differential is not 0.1 seconds, but 0.001 second. Okay, 49.0049. Okay, from the top end, what do you believe the instantaneous velocity to be? 49. 49. If I had to guess, and I could keep running values, and that's why I have this table here, because I'm a little bit of a cheater there, you can estimate the instantaneous velocity to be 49 meters per second. 49 meters per second. Now, obviously, could I have ran this from the bottom end and up? Yeah, I could have done that exact same thing. I could have gone with the time interval 4 to 5, then 4.5 to 5, or they went to 0.1, 4.9 to 5, then 4.999 to 5, and so on and so forth. But guess what? It would have gotten me something like 48.999. And we can estimate that it's going to converge to 49. Okay? So right now, if I want to find instantaneous velocity, the only way that I am able to do this right now, we will learn ways around it, but the only way that I am able to do this right now is to just run values and to estimate where it's going to go, to see, until you see a pattern, you have to keep running values. You can't just assume that it's going to go somewhere. You have to keep running values until you see a pattern. Until you see, okay, I have seen it now a couple of times over again. I believe that it's going to go there. Okay? You know what's interesting about this? You may have the feeling that these calculations used in solving this problem are very similar to those you used earlier in this section to find tangents. In fact, there is a close connection between the tangent line problem and the problem of finding velocities. You know, if we draw those graphs of if we draw the graph of the distance function of the ball, and we consider the points a and 4.9a squared, that's just like our plugging it in, right? Our function was 4.9t squared. They say, well, just use a, input a, output 4.9a squared. If we just generalize it, we don't say 5. We just generalize it. We said, okay, put in a differential. Put in like a unit of change. They're saying, okay, well, instead of plugging in a, plug in a plus h. Right? Well, what would that look like? Well, that would be 4.9 a plus h, oops, I forgot my h, squared. And what does this look very familiar to? Isn't that difference quotient? Isn't this the f of a plus h minus f of a all over h, really? Because what happens with my a's? Look at the bottom. Don't they cancel out? But this was for this unique function. What if I wanted to do this for any function? What if I didn't know that this was like a falling ball problem? Could I still apply that? Yeah, take a look. Sorry for the people watching along at home. I'm doing this on the whiteboard. Take a look. If I had f of x, and I didn't even know what it was, doesn't matter what it is. Okay. If I have a, the output is going to be f of a, right? And then I wanted to make a little bit of a difference in a. And I said, okay, I want it to be a plus h. the output would be f of a plus h. If I wanted to find the slope of those 2 points, I would take f of a plus h minus f of a, all divided by change in x, a plus h minus a. Right? Y minus y over x minus x, and I can see that those will cancel. Now, here's the cool thing about this. What was I doing with my difference in both of these problems? My differential, my difference on x values. I made it go from 0.5 to 0.25, and then I made it go to 0.1, like here. The time differential, I made it go from 1 to 0.5 to 0.1 to 0.001. What was I doing with my h value? What did I really want it to go to? 0. That's really what I wanted it to go to. And all of chapter 2 is, what we're doing here is we're actually taking a limit. Okay? What we're doing is we're taking this idea of a limit. I'm kind of getting into the next section. But this idea of making a value go to something, we're going to say let h go to 0. Okay, within this equation. And that's really honestly how you find the slope of any tangent line. You're going to run this equation and you're going to say, okay, run this equation, but in the end, turn h into 0. That's really what you want to do. And in doing that, you are finding instantaneous slope or instantaneous velocity. All right. And that is it for section 2.1, my friends. Really short, easy section for today to start out with. I wouldn't say easy. Conceptually difficult. But, writing-wise, not so bad. Let me stop my video here.